Hi Year 12, this is the third lesson for the topic of proof. In this video we're going to look at the divisibility type of mathematical induction questions. So far this topic we've looked at what is proof and the different types of proof. Then we looked at mathematical induction and the series type of mathematical induction questions. Here's our first example. Prove that 5 to the power of n plus 3 is divisible by 4 for all positive integers n. So we're going to follow the same procedure. Step 1, show that it's true for n equals 1. Now this time we don't have a left-hand side, right-hand side. I'm just going to substitute 1 in for n. So 5 to the power of 1 plus 3 is 8, and that is divisible by 4, so it is true for n equals 1. Step 2, assume that it's true for n equals k. Substituting the k in, I'm going to write 5 to the power of k plus 3 is equal to 4m, where m is an integer. And step 3, I want to prove it true for n equals k plus 1 using this assumption from step 2. All right, we're going to start by substituting k plus 1 in here. Now typically with these sorts of questions, I'm going to split this power. This is going to become 5 to the power of k times 5. Now I need to get this into play, so I'm going to make 5 to the k the subject. That will equal 4m take away 3, and I'm substituting that in here. Make sure that makes sense to you. All right, I'm going to expand this out. So that's 20m take away 15 plus 3, which is 20m take away 12. And factorizing, I have a common factor of 4, which shows that it is divisible by 4. So therefore it is true for n is equal to k plus 1. Therefore, it is true for all n. Let's try another one. Example 2. Prove that n cubed take away n is divisible by 3 for all integers n is greater than or equal to 2. So this time my initial condition is n equals 2. So step 1, show it is true for n is equal to 2. Let's substitute 2 in for n. 2 cubed is 8, take away 2 is 6, which is divisible by 3. Therefore, it is true for n equals 2. Step 2, let's assume it's true for n equals k. We're going to substitute k in for n. So in other words, k cubed take away k is equal to 3m, where m is an integer. Step 3, prove true for n equals k plus 1. So again, we're going to substitute k plus 1 in for n. So we get k plus 1 cubed, take away k plus 1. We're going to expand this out. We're going to do that by using our binomial theorem. Recall it is k cubed plus 3k squared plus 3k plus 1. And expanding this negative through the brackets, get minus k minus 1 here. Now I can make k cubed the subject here, but I can see a k cubed minus k sitting there. So just rearranging that, that's going to be 3m. And I have a common factor of 3, don't I? So therefore, it is divisible by 3. Therefore, it is true for n equals k plus 1. Therefore, true for all n. Example 3. I hope you're starting to get the idea. Prove by induction that n cubed plus n plus 1 all cubed plus n plus 2 all cubed is divisible by 9 for n is equal to 1, 2, 3, etc. All right, step 1. Let's show it's true for n equals 1. We're going to substitute 1 for n. So 1 cubed plus 2 cubed plus 3 cubed is 36. It is divisible by 9. Therefore, it is true for n equals 1. Now let's assume it's true for n equals k, and we'll substitute k for n. So k cubed plus k plus 1 all cubed plus k plus 2 all cubed is equal to 9m, where m is an integer. And step 3, prove true for n equals k plus 1. So starting the same way, substitute in k plus 1 for n gives us this. Now we could expand all of that out. It would be an absolute nightmare. Is there a better, more efficient way? Let's think about it. You see this, k plus 1 cubed, k plus 2 cubed. That's sitting there. Can you see it? How about I make that the subject? And that will be equal to 9m take away k cubed. And that's going to be much, much easier, isn't it? Now we still have to expand this out. This is going to be k cubed plus 3 times k squared times 3 plus 3 times k times 3 squared plus 3 cubed. Tidying that up, I end up with 9m take away k cubed plus 9k squared plus 27k plus 27, which is 9m plus 9k squared plus 27k plus 27, which has a common factor of 9. So therefore, it is divisible by 9. It is true for n equals k plus 1. Therefore, it is true for all n. And example 4, prove by induction that 9 to the power of n plus 2 take away 4 to the power of n is divisible by 5 for all n is greater than or equal to 0. All right, so step 1, let's show it's true for n equals 1. Substituting in, we are going to get 9 cubed take away 4, which is 725, which is divisible by 5. So it's true for n equals 1. Step 2, assume it's true for n equals k. In other words, 9 to the power of k plus 2 take away 4 to the power of k is equal to 5m, where m is an integer. Step 3, prove true for n equals k plus 1. So I'm going to substitute k plus 1 in here and in here, like this. And just like I did before, I'm going to split both of these up, but I'm going to try and match what I have here. So I'm going to get a 9 to the power of k plus 2 out of that, and a 4 to the power of k out of this. So I'm going to split the 4 off here and a 9 off here, like this. Now just pause for a second, make sure that makes sense. 9 to the power of 1 times 9 to the power of k plus 2 is 9 to the power of k plus 3. And 4 to the power of 1 times 4 to the power of k is 4 to the k plus 1. Now, I've seen many tutors try and match this exactly. I don't think that's the best way to do it. It's quite complicated. In fact, I'm going to make 9 to the k plus 2 the subject, just like I did in previous examples. So 9 to the k plus 2 is equal to 5m plus 4 to the k. And I'm going to substitute that in here. And that gives me 9 outside of 5m plus 4 to the k, in brackets take away 4 times 4 to the k. All right, when we're expanding this, you need to be really careful. This first bit is okay, that's 45m. But 9 times 4 to the k is not 45 to the power of k. I'm going to write it like this. So 9 5s are 45, and then the m, plus this is 9 lots of 4 to the k, and then I've got take away 4 lots of 4 to the k. You with me? Now we can tidy this up. If I've got 9 lots of something, take away 4 lots of something, that's 5 lots of that something, correct? And factorizing the 5 out, look what I have. 5 lots of 9m plus 4 to the k, so it is divisible by 5. So therefore it is true for n equals k plus 1, therefore it is true for all n. Okay, that's the end of our third lesson. Our last lesson on this topic is when mathematical induction doesn't work.